Here's a couple slides on infrared color selection. I'm going to start with sort of the general discussion, which has some kind of a historical flavor to it. Then we'll talk about the Gutermuth selection, and then we'll talk about the Koenig selection. So just a brief history. In 2004, Spitzer was brand new, and we had never looked at the sky with this telescope with these detectors before. And so there were several people, most notably Laurie Allen and collaborators, who did some simple theoretical models that combined the theory with IRAC filters and said, okay, young stars should kind of be here, and YSOs of, class 1s versus class 3s should be in this kind of spot or that kind of spot. I'll have some slides on these in a second. Because this seemed to work really well, the next group of people, such as Bill Reach and company in 2004, took this a step further and expanded it to include the MIPS bands. And as we had more and more data, real data from real star-forming regions and real galaxies, we started to notice patterns about where we were looking. And things in extragalactic fields should largely be lonely stars in the foreground, and then the galaxies have different distributions of colors than fields that are in the direction of star-forming regions. And so I have some examples from my paper on that. And the whole idea is you start to understand where objects should fall based on looking at things whose nature you already think you know. So this is the Allen et al. 2004 plot. So we've got 3.6 minus 4.5 in magnitudes on the y-axis, and 5.8 minus 8 in magnitudes on the x-axis. And so basically what they did was they drew lines in this diagram. So all the photospheres are here. The class 2s are in this box. Things that are between class 1 and 2 are over here. Class 1s are over here. Now, they've got some reddening vectors here. What that means is if there's a substantial amount of dust, because remember, the infrared dust doesn't affect you so much, but if there's a huge amount of dust, which there often is in star-forming regions, it's going to push these objects, in this case, redder in this direction, but slightly bluer in this direction because of something called the 10 micron feature. So all of these guys are heavily reddened class 2 objects who should really be back here, but the extra dust in the way is pushing them up in that direction. Much like sunsets appear red, it's the same physics. And the same thing is here. These are the class 1s, and these are the reddened class 1s. And the plain stars are here. So there are other similar, pretty simple cuts you can make in just one diagram. But if you're looking at a region that is around a star-forming region or a big field of almost anything, how can you be sure that what you're looking at is really a young star? So here's folding in MIPS. Here we have, 3.6 minus 5.8, IRAC 1 minus 3 on this axis, and 8, IRAC 4, minus 24, or MIPS 1 on this axis. Plain stars, again, of 0 color. You've got the debris disks here, and then things that are really red in both colors are class 2s or class 1s. So this is the next step. Okay, so now we have a big field in Perseus where there's known young stars, but there's also some galaxies. So what we did was we said, okay, here's the y-axis is K, the x-axis is K minus 24. So this is a color magnitude diagram. And this box here marked SWIRE. SWIRE was an extragalactic survey. So everything that was in the SWIRE field should either be a foreground star or a galaxy. And you can see there's so many points I've done them in contours. There's a whole bunch that have 0 color at a range of brightnesses, and there's a whole bunch that are very red and very faint. These are the galaxies. Those are the stars. So now we're going to look at 2 regions of star formation within this larger cloud as well as the rest of the cloud. And the gray are the things that we think are the back, just plain stars with no excess. The symbols here correspond to different detections. So if I remember correctly, the pluses are detected, and IRAC, all 4 IRAC bands, the additional square means it's detected at 24 microns. And I'm sorry, I don't remember what the triangles are. I'm sure it's some other detection that I'm indicating there. But you can see here that the distribution of sources, of colors of sources, for these two known star-forming regions are very different than what you get in the galaxy field. You get a whole bunch of things that are bright and red, and those are the young stars. And that's exactly what we did to make a guess as to what the young stars were in this cloud. And that's comparing the sources in our field to that of a population that we think we understand, that we know. So again, that's just the stars. So in an ideal world, what color selection you use depends kind of on what you're looking for and where you're looking. And things get messy because the regions of color space are not necessarily cleanly defined. And so you have to start making statistical estimates, guesses, like objects brighter than this are more likely to be young stars than objects fainter than it. You also want to use all the data you can find, not just two bands of IRAC, but everything you can find. And you want to be careful about the interlopers, things that you might mistake for a young star. There's a lot of things out there. So this is a WISE color diagram, and I'm sorry I can find an IRAC one quickly. 3.4 minus 4.6 on the y-axis, 4.6 minus 12 on the x-axis, and this is from an extragalactic discussion. So you can see there's lots of different kinds of galaxies, but they are highly overlapping in where you find them. And the T-dwarfs, the low-mass stars, have very different colors. And that's what they're calling out in this diagram. But you can see the stars are down here with zero color when we expect. But there's young stars all over the place, too, on top of these galaxies. So there could be a lot of things in your field, and you got to be careful. Here I have two different plots. One that's 5.8 minus 8 in IRAC versus 3.6 minus 4.5 from IRAC. Here's 3.6 minus 5.8 versus 8 minus 24. And note that she's got Vega magnitudes on the x-axis, but then for comparison, because she's an extragalactic astronomer, she's got the AB magnitudes also for reference. So she's collected here in this plot. Each one of these symbols represents a different population. She's got quasars, submillimeter galaxies, AGN, nearby galaxies from SINGS, planetary nebula from GLIMPS, the Galactic Plane Survey, two populations of AGB stars, asymptotic giant branch stars from the LMC, the Large Magellanic Cloud, Cepheids from our Milky Way, YSOs from a particular field in Cepheus, like we're using, white dwarfs, brown dwarfs, and asteroids. And they all overlap. It is tough to separate these different populations if all you have is 4 bands or less of IRAC. You want to try to use as much information as you possibly can to separate out these various populations. So this is just saying, again, you want to use data from as many different bands as possible. You want to use your experience with other regions, such as normal galaxies fall here, quasars fall there, AGB stars here. And so you want to use color cuts in more than one diagram. And if you want to work on this yourself, you need to use a big catalog so that you can see where most objects fall and then identify the odd ones. But I don't mean 10 or 50 objects, but I mean 100, 1,000, 10,000 objects so that you can see where the weird ones fall. So the color cuts that I've described are simple because they're usually just one part of one diagram. And when you use more data, you get more diagrams. And then you have to keep track of more things, like if it passed this test but failed that test. And you have to keep track of that bookkeeping fairly carefully. Also, equations that look complicated sometimes turn out to be really simple. You can try Googling that expression without the quotes around it. So here's Google. I'm going to put in that equation and search, and it makes the plot for me. So the blue spells out this heart. The red is the top of the circle, and the orange is the bottom of the circle. So it looks super complicated, but when you actually plot it out, it's not so bad. So that's a good thing to remember. Both Rob Gutermuth's approach using Spitzer data and Xavier Koenig's approach using WISE data have similar complicated looking equations, but all they're doing is describing line segments in these various spaces. So I don't think you should be intimidated by this. If you are, sit down and work through a few, even if it's just making a pencil and paper plot. It's not so bad. It just looks bad. There are 2 links here of other uses of math to describe simple pictures. This first one has math describing pasta shapes, And this was an article called "Don't Make Me Do This, the Equation Screamed." So you can see it's tongue-in-cheek, but the idea is that he's drawing pictures with the math. So, Rob Gutermuth's approach, and again, this is using Spitzer data. So, overall, you're going to make, for each possible color diagram that you can think of, you need to compare colors for each object, and you need to note the properties of that object in comparison to the ensemble and to known objects. And you have a big table, one entry per object, with the properties of this object in all these various combinations. And then you can make an educated guess, which are the YSOs. So we measured the properties of each object in all the bands that we could, and make plots and compare them in many different color spaces. We're going to do some of them when you're as part of our work, but in doing the Rob selection, the computer does it all without a human intervention. And the computer then makes educated guesses as to which objects are likely YSOs or contaminants, and it keeps track of which is which. So there's the first set of equations. Again, looks ugly. Not really. It's just 3 different line segments spelling out where those X's fall. So things that meet those criteria are likely to be background galaxies. Note them as such. Then do it again in a different parameter space. Things that meet these criteria are also galaxies. Drop things that meet these criteria and those criteria, because those are likely to be AGN. They're the ones over here. Drop the things that meet these criteria. These are likely unresolved blobs of dust. They look like point sources, but they're not, and their colors are largely shock emission. Keep things that meet these criteria and don't fail the earlier tests. These are the likely class 2s. Keep things that meet these criteria, and these are class 0s or 1s. Keep going. I've got more slides here that just are literally copies out of his paper of all of the steps. So he's measuring the extinction to the region, and then calculating the de-reddened near infrared colors, and then computing color ratios. Then add the things that meet these criteria to the YSO list. Add these things that meet these criteria to the YSO list. Add these things to the YSO list. And then check everything to be sure that they're okay. So you have to keep careful track of which objects pass or fail each test. And you should have 2 bins of objects in the end, possible young stars and likely junk. This cut isn't going to be perfect. There's going to be good YSOs in the junk and junk in the good YSOs. But statistically, you should be okay. There's not a ton of point in making a lot of work for ourselves by combing through the junk, because it's going to take a long time to find any that escaped our net. So we're going to focus our efforts on the possible young stars. But we're going to use data from many other bands. So you can see that Rob's method is really only using IRAC and 2MAS. We have much more than that, and we can use that other information to help us weed down the bin. Rob already ran his software for us on the CFC cryo era data, and it provides an IRAC-based selection. We have that cut. We're going to merge it to the list of things that are star-like and detected in X-rays, and to the things that are variable, and to the things that were identified in the H-alpha surveys as bright in H-alpha. And then we have that list of 250 or so objects. Now we have to go look at them. And we have to look in the images where we can, and the SEDs where we can, and assess whether or not we believe it as a young star. Xavier's method is similar, but is using WISE data rather than Spitzer data. We didn't use this for CFC, but I'm going to include it here because other teams have used Koenig's method, and as long as I'm making a video, let's make it a little bit more globally applicable. So here, too, he's got the same approach. Look at a region that's likely to be all galaxies. In his case, it was the ecliptic pole. Where do those sources fall? Are they galaxies? And play with some models to make sure that you understand why they're there. 3.4 minus 4.6 versus 4.6 minus 12. Plain stars and elliptical galaxies. And you've got spirals and irregulars. And you've got AGN up here. Okay, now we're going to look at a catalog of known young stars. Where do those objects fall? How do they compare to where the galaxies were? Let's draw lines around a region of the diagram containing only, or at least mostly, galaxies, so that any new objects we find in this funny polygon here are also galaxies and not young stars. Keep doing it. Here's 3.4 versus 3.4 minus 12. We're going to block out this part as likely galaxies. 4.6 versus 4.6 minus 12. Let's block out this part as likely galaxies. And then you can start to notice patterns of where the objects fall. Here's 3.4 minus 4.6 versus 4.6 minus 12. Plain stars in class 3s, class 2s, class 1s. And then keep doing it. Do it in all the parameter spaces you think are useful. Keep making those diagrams and keep cutting out the things you think are galaxies or foreground stars. And then you can start to make definitions of, okay, things that are in this diagram we're going to call class 1s. Things that are in that part we're going to call transition disks. So that's the basic approach. It's a series of cuts in color, and color magnitude spaces that statistically are weeding out the galaxies and the foreground stars, leaving us with the YSO candidates. It's not perfect, but it's a whole lot easier to look through 250 objects to decide which are the young stars versus all 30,000 objects or however many we have in any given chunk of sky. It's a lot easier to have the computer do that initial cut for us so that we don't have to do it by hand.